Hello everybody, my name is Taifat Trong from the Department of Chemical and Material Engineering at New Mexico State University. Today I'm going to present my project which specialized in internalizing the fluid behavior in a 2D pipe. As an outline, I'm going to quickly skate through the introduction applications of the given geometry in the chemical industries. Then a brief procedure on how to set up the parameters in CFD will be given. Then I'm going to present my result. With this project, the CFD program is employed to take care of the simulation, and the geometry can be considered as an inlet going through a compressor before entering the reactor. The first thing to set up the CFD is the geometry. Since it inherits a fairly complicated structure, I personally recommend connecting single lines altogether in conjunction with constants to complete the surface. Then I inserted a mesh network as the number of differential equations that I designed the software to solve to capture the behavior of the fluid inside. After exported the mesh network and imported it into the solution part of the program, the properties of the fluid are pre-specified, such as density of 1,000 km per cubic meter and viscosity of 7.5 centipoles. Reynolds number are then also calculated in advance to preliminary predict whether the fluid will constitute a laminar or turbulent flow. In case of turbulent, the K epsilon model will be employed to address the behavior. The program was then run to arrive at the following result. In regard of velocity contour, we have 5 figures illustrating the 5 different inlet velocity. As you can see, the fluid proceeds along the geometry due to changes in areas. They have different contours. For instance, in section 4, where the area is largest, the fluid is evident to move most slowly in that section. Then due to being squeezed down, the fluid accelerated in the final section. As the model scale up, the fluid behavior does not seem to change quite a lot. The fluid just moves more quickly, as shown by the lighter shade of blue in the contours. Then some of you may come to the concern how long the fluid takes to reach to the fully developed state. The concern is unraveled by the hydrodynamic entrance length. Taking the inlet velocity of 0.01 meter per second into account for a set of 5 lines in the first section where I wanted to see the velocity profiles. The velocity profiles start overlapping around the 5th line, indicating the entrance length to be around 1.5 times 10 to the negative 4, which is exactly at 1/10 of the first section. Pressure seemed to be an interesting point to discuss as well, which brings us to the next step. To the next topic. For low scale, pressure drop is quite monotonous, but show a pretty pattern where the pressure drops gradually along the pipe and no backflow occurs. On the other hand, for scale-up model, pressure changes in a more arbitrary manner, decrease at first and then increase. Due to the bizarre increase, backflow is very likely to present at the pre-precursor. Finally, let's discuss about the fluid behavior in section 4, the most troublesome area of all, as expected from the heel leap in the area velocity will respond in a drastic drop, which includes circulation in section. This problem can be solved. As shown in the given figure, at high velocity, the circulation remains incurring, but in the very last part of the section. Therefore, to abandon circulation, the velocity of the fluid has to exceed the threshold velocity, which is calculated and given in the following table. At the bottom of the report, I construct a line at the middle of each section to capture the velocity profile. The result is as follows. Thank you for listening, and that's the end of my presentation.